Hello everyone, I'm Dr. Abhina Shirley from the Department of ECE at SRM Institute of Science and Technology, Katangalattu. Welcome to Unit 3 on Cloud Storage Systems. In this unit, we are going to understand how massive amounts of data are stored, managed, and accessed efficiently in cloud environments. We will begin with storage models and file systems, then move into distributed storage technologies such as Google File System and Apache Hadoop. After that, we will discuss online transaction processing systems and understand the importance of real-time transaction handling. Finally, we will explore modern NoSQL cloud databases like Apache HBase, MongoDB, and Apache Cassandra. Overall, this unit helps us understand how cloud platforms manage huge volumes of data with scalability, reliability, and high performance. Now let us understand why cloud storage has become so important in modern computing. In cloud computing, storage and processing always work together. Cloud applications do not just store data, they continuously process huge amounts of information in real time. For example, applications like YouTube, Netflix, and social media platforms, online shopping sites, and banking systems generate enormous amount of data every second. Because of this, cloud platforms require efficient storage management and data replication techniques to ensure fast and reliable access. Another important requirement is reducing access time. Users expect videos to stream instantly and services to respond immediately. So, cloud systems use advanced strategies to support real-time multimedia access and fast content delivery. This slide also mentions sensors generating continuous streams of data. This refers to IoT devices such as smartwatches, health monitoring systems, industrial sensors, and smart home devices. These devices constantly send data to cloud applications for processing and analysis. In addition, many cloud-based services collect detailed information about user behavior and service usage. Companies analyze this data to improve recommendations, advertisements, and customer experience. Finally, the slide highlights the massive scale of global data generation. Internet video traffic and mobile data traffic are growing tremendously, reaching exabytes of data every month. This clearly shows why scalable and efficient cloud storage systems are essential today. Logical and physical organization of a file. Before understanding advanced cloud storage systems, we first need to know how a file is actually organized inside a computer system. A file can be considered as a linear collection of data cells stored permanently on a storage device like a hard disk or SSD. To an application, the file appears as a collection of meaningful records such as text, images, audio, or database entries. Internally, however, the storage device does not store the file as one continuous object. Instead, the file is divided into smaller units called physical records or blocks. These blocks are stored on the storage media according to the storage structure. Another important concept is the file pointer. A file pointer simply indicates the location from where a read or write operation should begin. Whenever we open a file or edit data, the operating system uses this pointer to access the correct position. Now, file organization can be viewed in two different ways. One is the logical organization and the other one is physical organization. Logical organization represents how the application or user views the data. For example, a student database may logically appear as rows containing name, roll number, and marks. Physical organization describes how the same data is actually stored inside the storage device using blocks and memory locations. So, in simple terms, logical organization focuses on user understanding while physical organization focuses on actual storage implementation. Now, let us move to the concept of file systems. A file system is responsible for organizing and managing files inside a storage device. It maintains directories, file names, storage locations, and access information so that users and applications can easily store and retrieve data. Traditionally, systems called the Unix file system, which worked well for standalone computers, but in cloud computing, data is distributed across multiple machines, so distributed file systems become very important. One commonly used distributed system is the network file system. In this approach, files stored on one machine can be accessed by another machine through a network. Although NFS became very popular, it has some limitations. It does not scale efficiently for very large scale environments, and if the NFS server fails, the entire service may become unavailable because the server acts as a single point of failure. Another approach is the Storage Area Network or SAN. Here, the storage devices are connected through a dedicated high-speed network. Storage resources can be pooled together and allocated dynamically based on server requirements. This provides flexibility and non-disruptive storage management. However, storage area network systems are expensive because specialized hardware such as fiber channel adapters are required. To overcome scalability issues, parallel file systems were introduced. These systems distribute files across many storage nodes and allow multiple nodes to serve data simultaneously. They also include a metadata server that maintains information about file locations. Because many nodes work together in parallel, these systems provide high scalability and faster data access, making them suitable for large cloud infrastructures. Let us now understand the Unix file system, commonly called UFS. One important feature of UFS is its layered design. This layered approach gives flexibility because it separates the logical view of files from the physical storage details. In simple terms, users see files and folders in an organized manner, while internally the system manages storage blocks and memory locations separately. The Unix file system follows a hierarchical tree structure. At the top is the root directory represented by a slash symbol. From this root directory, all other directories and files are organized in branches just like a tree structure. At the storage level, files are divided into blocks. These blocks are the basic units used to store data on the disk. The file system keeps track of these blocks and manages how data is stored and retrieved efficiently. Another important concept is the inode or INEX node. Every file has an inode associated with it. The inode stores metadata such as file permissions, ownership, file type, and pointers to the actual data blocks. So the inode acts like an information record about the file. Next comes the path name layer, which defines how files are addressed. Paths can be absolute or relative. An absolute path starts from the root directory and specifies the complete location of a file. For example, slash home slash user slash document slash file dot text. A relative path, on the other hand, specifies the location relative to the current working directory. Overall, UFS provides a structured and efficient method for organizing and accessing files within a system. Continuing with the Unix file system, let us understand a few more important layers and structures. One useful feature in Unix systems is the symbolic path name, also called a symbolic link. A symbolic link acts like a shortcut that points to another file or directory. Instead of storing duplicate data, the system simply creates a reference to the original file location. Next comes the file name layer. This defines the naming conventions used for files. File names can include letters, numbers, and certain special characters, allowing users to organize files meaningfully. Now let us clearly differentiate between logical file structure and physical file structure. The logical file structure represents how users and applications view the data. It includes files, directories, subdirectories, and symbolic links arranged in an hierarchical structure. Directories act like containers that hold files and other folders. The physical file structure focuses on how data is actually stored inside the storage device. Internally, the system uses disk blocks, inodes, and allocation mechanisms to manage storage efficiently. Disk blocks are the smallest storage units on a disk. When a file is saved, its contents are divided into these blocks and stored at different physical locations if necessary. So overall, the logical structure helps users interact with files easily, while the physical structure ensures efficient storage and retrieval inside the hardware. Unix file system layering. Here we can see the layered architecture of the Unix file system. The topmost layer is the or application layer. Users interact with files through commands or applications without worrying about how the data is physically stored. Below that comes the file name layer, which manages file names and directory structures. This layer helps users locate files using readable names instead of physical storage addresses. Next is the symbolic pathname layer and pathname layer, which handle navigation through directories and file paths. These layers help the system interpret absolute and relative paths correctly. Then comes the high node layer. This is a very important layer because it stores metadata about files such as permissions, ownership, file size, and pointers to data blocks. Below the inode layer is the block layer where the actual file data is divided into storage blocks. The operating system manages these blocks for efficient storage and retrieval. Finally, at the bottom, we have the physical storage device such as a hard disk or SSD where the actual data blocks are permanently stored. This layered structure makes the Unix file system flexible and efficient because each layer performs a specific function independently while working together as a complete storage system. Now let us move to the network file system commonly called NFS. NFS follows the client-server model. In this approach, one system acts as a client requesting files, while another system acts as the server storing and providing those files over the network. The communication between the client and the server happens using Remote Procedure Calls or RPC. This allows a client system to access remote files as if they were stored locally. A host simply refers to a computer connected to a network. In NFS, some host functions as clients and others function as servers. Applications running on the client system may require access to shared files. These applications interact with the file system through the File System API interface, which provides functions for reading, writing, and managing files. Next comes the vNode layer. This layer manages metadata associated with files and directories, including permissions, ownership, and file types. The NFS client is responsible for accessing remote files from the NFS server. It sends requests and receives data through the network. Another important component is the NFS stub. The stub acts as an intermediary between the local file system interface and the NFS protocol. It converts local file requests into network requests and converts responses back into a format understood by the local system. Overall, network file system allows multiple computers to share files efficiently over a network, making remote storage appear similar to a local storage. Let us continue with the remaining components of the network file system. A remote host refers to the system connected through the network that provides NFS services. This server stores the shared files and directories that clients can access remotely. The communication network connects the client and the server systems. This network may be a local area network, wide area network, or even the internet. It enables the transfer of file requests and responses between the systems. The NFS server plays a major role in managing shared resources. It exports its local file system so that remote clients can access files over the network. Whenever a client requests data, the NFS server processes the request and sends the required file information. On the client side, there is also a local file system. This refers to the files and directories physically stored on the client machine itself. The remote file system refers to the storage shared by the NFS server. Even though the files are physically stored on another machine, the client can access them almost as if they were local files. So overall, NFS creates a transparent file sharing environment where multiple systems can communicate and share storage resources efficiently across a network. Now let us understand the working of the network file system architecture using this diagram. On the left side, we have the client host where the user application is running. The application sends a file access request through the file system API interface. This request then passes through the vNode layer, which manages file-related metadata. Next, the request reaches the NFS client and the NFS stub. The stub converts a local file operation into an NFS protocol request suitable for network communication. This request is then transmitted through the communication network to the remote host, which acts as the NFS server. On the server side, the NFS server receives the request and interacts with its local file system where the actual shared files are stored. After accessing the required file or data, the server sends the response back through the network to the client system. Finally, the requested file becomes available to the application running on the client host. So even though the file physically exists on a remote server, the client system can access it in a seamless manner, almost like a local file. This is the major advantage of the network file system. Now let us move to the Google File System, commonly known as GFS. GFS was developed by Google in the late 1990s to handle extremely large amounts of data generated by Google services. Instead of using expensive high-end hardware, GFS was designed using thousands of inexpensive commodity computers working together as a cluster. The main goal of GFS was to provide scalability and reliability while managing petabytes of data for millions of users. One important design consideration was scalability. As the amount of data grows continuously, the system should easily expand by adding more storage nodes. Reliability was also critical because failures are very common in large distributed systems. Since thousands of machines are involved, some systems may fail at any time. GFS was designed to continue functioning even during such failures. Another observation was that most operations involved appending data to existing files rather than modifying data randomly. For example, logs and search engine data are continuously added to files. Users generally process data in bulk, meaning they handle very large data sets together instead of accessing small pieces of data frequently. Because of this, response time for individual requests is less important compared to overall throughput. To improve efficiency, files are divided into large chunks. This reduces metadata overhead and improves storage performance. GFS also uses a master node to control critical operations and maintain consistency across the entire system. Finally, efficient garbage collection mechanisms are included to remove unused data and manage storage efficiently. Let us now understand the architecture of the Google File System cluster. At the center of the architecture is the master node. The master acts as the controller of the entire GFS system. It maintains metadata information such as file names, chunk locations, and access permissions. It also coordinates communication between clients and chunk servers. The actual file data is stored inside chunk servers. Files are divided into large chunks, and these chunks are distributed across multiple chunk servers in the cluster. Since data is replicated across different servers, the system remains reliable even if one server fails. On the client side, applications first contact the master to obtain metadata information such as the location of the required chunk. After receiving the chunk location details, the client communicates directly with the chunk servers to read or write data. This reduces the workload on the master and improves overall system performance. The architecture also separates control flow and data flow. The master mainly handles control operations and metadata management, while the chunk servers handle actual data transfer. This distributed architecture allows GFS to provide high scalability, fault tolerance, and efficient handling of massive datasets. Let us now understand how data is actually stored in the Google file system. In GFS, the files are divided into fixed size segments called chunks. Each chunk has a size of 64 megabytes. This large chunk size helps improve performance when handling very large files and also reduces the amount of metadata the system needs to maintain. Because the chunks are large, multiple operations are likely to access the same chunk repeatedly. This reduces the number of requests sent to local chunks and also allows applications to maintain persistent network connections with chunk servers, improving efficiency. Internally, each chunk is further divided into smaller blocks of 64 kilobytes. Every block contains a 32-bit checksum used for error detection and data integrity verification. These chunks are stored on Linux file systems and replicated across multiple chunk servers. Replication is important because it provides fault tolerance. Even if one server fails, copies of the chunk are available on other servers. Whenever a new chunk is created, the system assigns its unique chunk handle for identification. The master node maintains metadata and state information about all chunks and chunk servers in the system. It controls the chunk servers and keeps track of chunk locations. The chunk servers themselves communicate directly with client applications for actual data transfer. This avoids overloading the master with data operations. In the architecture diagram, the thick lines represents the data path, meaning the actual transfer of file data, while the thin lines represents the control path used for coordination and metadata management. Overall, this chunk-based architecture helps JFS achieve high scalability, efficient storage management, and reliable distributed data access. Two highly desirable properties of any storage model. Whenever we design a storage system, especially in cloud computing, there are very two important properties that ensure reliable and consistent data handling. The first property is read-write coherence, and the second property is before or after atomicity. These two properties are extremely important in distributed cloud storage systems because multiple users and applications may access the same data simultaneously. Without these properties, inconsistencies, incorrect updates, and data corruption can occur. So, reliable cloud storage systems are always designed to maintain both coherence and atomicity while handling massive concurrent operations. Let us see them in detail. First, rewrite coherence. Suppose you update a file or save a new value into a database. Immediately after the write operation, if another user or application reads the data, they should receive the latest updated value and not an older version. For example, imagine updating a profile picture on a social media platform. Once the upload is completed, everyone accessing your profile should see the new picture instead of the old one. This is the idea behind the read-write coherence. Now, let us move on to before or after atomicity. Consider a banking example with two processors operating on the same account. Process A deposits $100 into the account while process B withdraws $50. Without atomicity, these two operations may overlap incorrectly. The withdrawal may occur before the deposit is fully recorded, resulting in an incorrect account balance. Before or after atomicity, the system guarantees that one operation completes fully before the other operation begins. So either the deposit happens first and then the withdrawal, or the withdrawal happens first and then the deposit. This ensures consistency and correctness in the final balance. These properties are extremely important in cloud databases and distributed systems where many users may access and update data simultaneously. Now, let us discuss Apache Hadoop, one of the most widely used frameworks for big data processing. Hadoop is an open source Java based software framework designed to store and process extremely large volumes of data across distributed computer clusters. Many major organizations use Hadoop because it can efficiently manage huge data sets at low cost. Companies such as Apple, IBM, Microsoft, Amazon, and Yahoo use Hadoop for large scale data processing. It is also widely used in media companies, social networks, and government agencies. A Hadoop system mainly consists of two important parts, the processing engine and the distributed storage system. The processing engine is based on the MapReduce programming model, which divides large computations into smaller parallel tasks for efficient processing. The storage component can use systems such as the Hadoop Distributed File Systems or HDFS as well as other cloud storage systems like Amazon S3 or CloudStore. HDFS is a distributed file system written in Java. It is designed to store data across multiple machines while providing high performance and fault tolerance. Although HDFS is highly efficient for big data applications, it is not fully POSIX compliant and cannot be directly mounted like a traditional operating system file system. Overall, Hadoop became very popular because it enables scalable, reliable, and cost-effective big data storage and processing in cloud environments. Let us now understand how a Hadoop cluster works using HDFS architecture. In a Hadoop cluster, data is stored across multiple machines instead of a single server. This distributed approach improves scalability and fault tolerance. At the top of the architecture, we have the client or the user application. The client submits data storage or processing requests to the Hadoop system. The central component is the name node. The name node acts as the master of HDFS. It manages metadata information such as file names, directory structures, permissions, and locations of data blocks stored across the cluster. The actual data is stored in data nodes. These data nodes are worker nodes responsible for storing file blocks physically on the local storage devices. When a file is uploaded into HDFS, it is divided into smaller blocks and distributed among multiple data nodes. These blocks are also replicated across different nodes to provide fault tolerance. So even if one node fails, the data can still be recovered from another replica. During data access, the client first contacts the name node to obtain the block location. Then the client directly communicates with the corresponding data nodes to read or write the actual data. This architecture allows Hadoop to efficiently process massive data sets in parallel while maintaining reliability and scalability. Let us now look at the major modules present in the Apache Hadoop framework. The first module is Hadoop Common. This contains the basic libraries and utilities required by all other Hadoop modules. It acts as the foundation for the entire Hadoop ecosystem. The second module is HDFS or Hadoop Distributed File System. HDFS is responsible for storing data across multiple commodity machines in a distributed manner. It provides high bandwidth and reliable storage for large-scale data processing. Next comes YARN, which stands for Yet Another Resource Negotiator. YARN is the resource management and job scheduling component of Hadoop. It manages computing resources in the cluster and allocates them to different applications efficiently. Another important module is MapReduce. This is the programming and processing model used for handling large data sets. MapReduce divides a large task into a smaller parallel task and processes them across multiple nodes in the cluster. Apart from these core modules, Hadoop also supports several additional tools and frameworks. For example, Apache Hive is used for SQL-like querying, Apache Peak simplifies data processing, Apache HBase provides NoSQL database support, and Apache Spark enables fast in-memory processing. Other tools like Apache Zookeeper, Apache Scoop, and Apache Flume further extend Hadoop's capabilities. Together, these modules make Hadoop a powerful ecosystem for big data storage, management, and analytics. With this, we come to the end of part 1 of Unit 3 on cloud storage systems. The next subsequent topics will be continued in part 2. Thank you.